In this lecture, we'll talk about the Burrows-Wheeler transform and the FM index. So we've already talked about suffix indexes like the suffix tree and the suffix array. And what we're going to find is that these are some new tools that we can use to make an index, and that the index will be surprisingly small, but still able to do many of the things that those other indexes do. So let's get started. So the Burrows-Wheeler transform is a reversible permutation of the characters of a string. And this idea, the Burrows-Wheeler transform idea, was originally used for compression. And I'll tell you a little bit later about how it was used for compression. So let's say we're starting with a string t over here, and it has our $sign at the end. The $sign means what it always means. It's a character that's less than all the other characters in the alphabet, and that does not appear anywhere else in t. And we're going to take this t, and we're going to produce all the distinct rotations of t. And by that I mean all the different ways that we can make a new string by taking a character off of one end of t and sticking it on the other. So this is t here. We can make a rotation of t by taking this a and going bloop, taking it off the beginning and then sticking it on the end. And then we would have the string $sign A. That's an example of a rotation of t. So we'll take all the distinct rotations of t and then sort them lexicographically, and what we get is a matrix like this, which is called the Burrows-Wheeler matrix. So every row of this matrix is a rotation of t, as you can see. And then the Burrows-Wheeler transform is simply the final column of this matrix, read off from top to bottom. So the Burrows-Wheeler transform of t is A, B, B, A, $sign A, A. All right? That's the Burrows-Wheeler transform. Now, there are a lot of questions that we need to answer about this. So I've showed you the transform. I've showed you it going in the forward direction. In other words, we took a string and we found its transform. I told you that it was originally developed for compression, and I don't think it's obvious yet exactly how you can use this for compression. I've also told you that it's reversible, but it's not obvious how you would get from this string back to the original string. And at the beginning, I said we're ultimately going to use this to build an index, like a suffix tree or a suffix array. It's also not clear how we would use it for that purpose, so I'm going to be making all those things clear. So here I have an implementation of the Burrows-Wheeler transform. It's a very simple implementation, meant really just for illustrative purposes. I wouldn't recommend actually implementing it this way. It would be very slow. But it's divided up into these three functions. So this first function just takes a string t as input and then produces a Python list of all the rotations of the string t. This second function takes a string t and then returns the Burrows-Wheeler matrix for t, which, remember, we said that all the Burrows-Wheeler matrix was just all of the rotations of t in sorted order. So all this really does is return Python sorted of rotations of t. So that's the Burrows-Wheeler matrix. And then this third function, given t, will return the Burrows-Wheeler transform of t. And it does that in terms of the functions above. So basically all it's going to do is take the Burrows-Wheeler matrix of t and then map this function to it, which basically just takes the final, character of every row and then joins them all together, so that you're essentially getting the characters of the final column of the Burrows-Wheeler matrix all together in a string. Now, it gets a little bit more interesting when we look at what the Burrows-Wheeler transform versions of some strings are. So that's what I'm showing you down here. So I'm showing you the output that you get when you run this function on some real strings. Okay, so here's the first example. And you can see the string that I'm giving it is somewhat repetitive, right? It's got some repetitive sequences of characters in there. And this is what the Burrows-Wheeler transformed version of that looks like. And what you'll notice is that some characters are coming together in runs like this. Like here's a run of 6 R's in a row. And here's a run of 3 O's in a row, and then there's a few more O's here. But you can just, if you cast your eyes over it, you can just see that the way we've transformed it, it's had a tendency to bring like characters together into runs. And we can see this in some other examples. Here's another string, input string. It's, perhaps not quite as literally and repetitive, but there are some repeats in here. And we can see, again, that there are some stretches of repeated characters in the transform version of the string. So here's 4 T's in a row, for example. And then here's a third example. Again, we see repeated characters in here. So one of the things that the Burrows-Wheeler transform seems to be doing is bringing like characters together into runs. So here's another example that shows what the Burrows-Wheeler transform is doing. So what I'm showing you here, it's actually a figure from the original paper describing the Burrows-Wheeler transform by Michael Burrows and David Wheeler. And what they're showing you here is, what you see here is text from their own paper, but it's in a Burrows-Wheeler matrix. So you can think of what's here as being like a little chunk out of the Burrows-Wheeler matrix. And it's a chunk out of the first several columns of the matrix. So this here is the first column of the Burrows-Wheeler matrix. And then here's second, third, fourth, fifth, etc. So that you can see at the beginning of each of these rows there's some recognizable text. But they all begin with N, because that happens to be the part of the Burrows-Wheeler matrix that they extracted in order to make this figure. And then what you see in the first column here is actually what you would find if you looked all the way in the last column of those rows in the Burrows-Wheeler matrix. So this, in other words, is part of the Burrows-Wheeler transform of the text T. And what you can see is, again, we see a phenomenon whereby there's a certain sort of tendency for like characters to come together into runs. There's something else these characters have in common, which is that they're all vowels, right? And this is not surprising when you consider how the Burrows-Wheeler matrix is sorted. It's sorted by rotation, which means it's sorted by these strings. And these are the strings that come immediately after these characters in the text. In other words, somewhere in the text it says an to decompress and on to perform. So this A comes before this N in the text. But it's sorted by this text. So another way to think of the Burrows-Wheeler transform of T, of that permutation of T, is that you're putting the characters of the text in sorted order, but sorted according to the stuff that comes right after. Sorted according to the right context, I'll call it, of every character in T. And when you sort by right context, that's why you tend to get like characters coming together into runs. And in this particular example, because it's English, it's even more interesting. We can see that before N's, we tend to see vowels, right? The thing that we see before the character N tends to be a vowel. And that's why we see nothing but vowels here in this part of the Burrows-Wheeler transform of T. Right? So another way of saying what the BWT does is that it sorts the characters of T by their right context, by the text that comes right after them in the string T. And this is what makes it more compressible. You can sort of see, if this is what we get out of the Burrows-Wheeler transform, and then our next task is to find a very concise way of storing this data, the fact that like characters are coming together into runs is going to be an advantage. So, for example, one very simple way that we can compact a string like this that has lots of repeated characters is with something called run length encoding, where basically if we see a stretch of 100 characters in a row that are all the same, we don't have to keep all 100 of those characters. We can just keep one of them and then add a little note that says there's 100 of these. That's one example, but there are actually many ways that you can take a string like this and compress it very effectively. So the Burrows-Wheeler transform, because it sorts by right context, tends to bring like characters together into runs, and this tends to make the text more compressible. Now, one thing I want to point out about the Burrows-Wheeler matrix is that it has a certain resemblance to the suffix array. In fact, the order in which we put the rotations, when we sorted the rotations, is exactly the same as the order we would put the suffixes in if we sorted the suffixes. This makes sense. It makes sense especially when you think about the dollar sign, right? The dollar sign, because the dollar signs are in there, if you think about the relative order of any two of these rotations, it only really depends on the characters up to and including the dollar sign. It does not depend on the characters that come after the dollar sign. Because if you compare two strings, two rows of this matrix, and you're comparing it to see which one's less than the other, and so you start doing character comparisons starting from the left and moving to the right, as soon as you see the first dollar sign in one string or the other, let's say we're comparing these two strings here. So as soon as we get to this position and we see this dollar sign, the tie is broken and we know the relative order of those two strings. We didn't have to look at any of these characters after the dollar sign in either string. And that's true in general. It just doesn't matter when you're sorting these strings. It doesn't matter what characters are coming after the dollar sign. So this order, the order of the suffixes in the suffix array, and this order, the order of the rotations in the Burrows-Wheeler matrix, are exactly the same order. And in fact, this suggests another way that we can find the Burrows-Wheeler transform of a string t. We can do it sort of via the suffix array, so that instead of actually constructing what we did before when we implemented that Python code, is we explicitly constructed all of the rotations of t and then we sorted them and then we took the final column. What we can do instead is build the suffix array of t. The suffix array tells us the lexicographical order of all the suffixes. So to get the Burrows-Wheeler transform, we just basically take the character that was just to the left of each suffix. So the first suffix lexicographically is the one that consists of just dollar sign. So we would just go look and see what's the next character to the left in t, and the answer is A. And so A becomes the first character of the Burrows-Wheeler transform of t. Likewise here, the second suffix lexicographically is a dollar sign. So what comes before a dollar sign in t? Well, it's B. So this is another way to build it. And here's a relation that's showing you how to construct each element of the BWT vector from elements of the suffix array vector. And the only special case, basically, is that when we get to the 0th suffix, when we see that this is the 0th suffix, instead of going to the left, we have to sort of like wrap all the way back around to the dollar sign. So the special case is that if the suffix array at element I is 0, then the Burrows-Wheeler transform at element I is going to be the dollar sign. All right, so here's an implementation using that different idea for how to build the Burrows-Wheeler transform. So here is a function called suffix array of s, and all it does is it builds the suffix array of that input string s and returns it. And the suffix array is just that list of indices. It's the permutation of the numbers 0 up to m according to the lexicographical order of those suffixes, right? So that's what that function returns. And now here's a new function that also, like the function I showed you before, calculates the Burrows-Wheeler transform of the string t, but this time it does it via the suffix array. So it initializes this new array where it's going to hold the Burrows-Wheeler transform. Then it iterates over all the elements of the suffix array. In this special case where the element is 0, it's going to append a dollar sign. Otherwise, it's going to append the character right before that offset, and then return the join of all those characters. Okay? So if you take that function and run it on the same examples, hopefully you should get the same output, and indeed you do get the same output. So this is another way of doing the Burrows-Wheeler transform. Okay, so a question that we asked before but that we haven't answered yet, we can see how we get from t to BWT of t, and we've done it two different ways. Now we want to know, how do we get from the BWT of t back to t? And that does not seem totally obvious. The way we're going to do it is via an important property that this matrix has, which is called the LF mapping. And the LF mapping is a relationship between the characters that you can see in the first column of this matrix and the characters that you can see in the last column. That's why it's called LF. It's for last first. So what is that relationship? So first of all, let me say that because we're dealing with permutations, and because these strings have repeated characters in them, I want to introduce a notion that's going to be helpful to us. Instead of just having these characters be in no way annotated, and therefore when they get permuted, you can't really tell which character corresponds to which original character, I want to introduce the notion of a ranking. And I'm going to introduce a particular kind of ranking first called the T ranking. And all I really mean by a ranking is a way of giving subscripts to the letters in the string so that we can tell them apart after we've done something to the string, like after we've permuted the string, for example. So in the T ranking, we're going to give each character in the string T a rank, and we'll draw it as a subscript. And the rank is just equal to the number of times that character occurred previously in T, earlier in T, and we're going to call that the T ranking. So for example, if this is T, then the way we're going to give the characters ranks are, well, this is the first A, and we're going to start at 0, so that gets a rank of 0. This is the first B, so that also gets a rank of 0. Now we reach this A, this is the second A, so this gets a rank of 1, and this A gets a rank of 2, and this B gets a rank of 1. We've seen 1B previously, and then this A gets a rank of 3. And we could give the $sign a rank, but it doesn't matter. It'll always be 0. So that is the string T, but annotated with its T ranking. And I want to emphasize that the ranks, I'm not suggesting that these are things that we store. I'm not suggesting that along with every character we also store an integer, which is its rank. Right now, I'm only using these ranks as illustration, again, so that we can tell the letters apart before and after the permutation. We know which letter is which. Okay, so now let's look again at the Burrows-Wheeler matrix, except now we have all the characters annotated with their T ranking, right? So all the nucleotides here, all the A's and B's here are annotated with a rank. Okay. Now let's ignore the middle. We'll ignore all these columns here. And what we're left with is the first column and the last column of the Burrows-Wheeler matrix. We'll call these F and L. So F refers to the first column, L refers to the last column. And now let's hide even more. Let's hide everything but the A's in the first column and in the last column. We'll just look at these A's. Now you might notice something about these A's, specifically about the A's and their respective rankings, which is that they occur in the same order if you read them off top to bottom in the first column as they do in the last column, right? So if you read the A's in this first column, it's A sub 3, A sub 1, A sub 2, A sub 0. Over here it's A sub 3, A sub 1, A sub 2, A sub 0. Same order. If you look at just the B's now, same thing. B sub 1, B sub 0 here, B sub 1, B sub 0 here. So it turns out this is true in general. And this is what the LF mapping property says. So the LF mapping property says that the ith occurrence of a character C in L, the last column, and the ith occurrence of a character C in F, the first column, correspond to the same occurrence of that character in T. In other words, they have the same rank. Another way we can say that is, however we rank occurrences of C, the ranks appear in the same order for the same character as we look down F and as we look down L. And we just saw that here. But we can just sanity check that. So like, for example, here's A sub 2. What the LF mapping property down here is telling us is that the third A in the first column should correspond to the same A in the original text. In other words, it should have the same rank as this A here. Boom, boom, boom. Yes, A sub 2. Now, why is this true? Why does the LF mapping hold? It's not too hard to see. So let's concentrate again on these A's right here in the first column. And again, I have them ranked according to their T ranking here. So if you think about it, why are these A's in this order? Why are they in this particular relative order? Well, it's because the whole matrix is sorted by rotation, which means that these A's appear in that order because of the relative order of their right contexts over here. right? They're in that order because they're sorted by their right context. All right? Now let's look at these A's over here, the A's in the last column. Why are these A's in this relative order? Well, these are in the last column of the Burrows-Wheeler matrix, so they're being sorted by the characters that come to the left of them in the Burrows-Wheeler matrix, but those are also their right contexts, right? So this string here, and this string here, and this string here, and this string here, those strings are in that relative order because the entire matrix is just a sorted list of rotations. So why are these A's in this order relative to each other? Again, because they're sorted by their right context. So if you pick a character and look at the occurrences of that character in the first column and think about why they're in that order, it's because they're sorted by their right context. And then if you do the same thing for all the occurrences of that character in the last column and think about why they're in that relative order, same thing. They're sorted by their right context. So we can say occurrences of C in the first column F are sorted by their right context, and the same is true for L. And therefore, whatever ranking we gave to these characters, the particular ranking doesn't matter. As long as each character has a distinct rank, the particular ranking doesn't matter. We'll see the same rank orders in F and L. Okay, so here's an alternative to the T ranking. So I'm showing you the T ranking here. But we want to try a different ranking, and we want the new ranking to have the property that if we look down the last column or look down the first column, we want to see for a given character the ranks be in increasing order. So we would want this to be A sub 0, and this to be A sub 1, and this to be A sub 2, and this to be A sub 3. And likewise, we want these to be A sub 0, 1, 2, 3. So let's define a new ranking that does this. This is called the B ranking. So this is a new ranking. And you can see this ranking does have that property. Basically, that's how I assigned ranks, so that this would be the case. So that if we just look down the last column, we see A sub 0 before A sub 1, before A sub 2, before A sub 3. And then, of course, by the LF mapping property, we see them in the same relative order here in the first column, too. Ascending rank as we go down. So notice something about F now, the first column. It has this very simple structure. Right? Again, because the whole matrix is sorted lexicographically, this first column is going to just be chunks of characters from lexicographically first, $ is always first, so that's always here, to the next highest, here's our chunk of A's, to next highest, here's our chunk of B's. So if this were DNA, for example, the first column would be $, and then a chunk of A's, and then a chunk of C's, and then a chunk of G's, and then a chunk of T's. But now, with this new ranking, with the B ranking, there's something also predictable about the order in which the ranks appear. They're going to appear in ascending order. So this block of A's is always going to be A sub 0, A sub 1, A sub 2, A sub 3, etc. So F now has this very predictable, very nice structure. And this is helpful to us, as we'll see. All right, here's where we can see why that's helpful. So now I'm showing you just L, just the last column. I've got rid of F, I've got rid of the rest of the matrix. And we're asking the following question. So here's B sub 1, the B of rank 1. Which Burrows-Wheeler matrix row begins with B1? So if we drew out that whole matrix, one of the rows would begin with B1. In other words, one of the characters in the first column would be B sub 1. So which one is it? Well, we can calculate this, again, because the first column has that very predictable structure. We know that it's a $, followed by all the A's, followed by all the B's, and that each section is in order by ascending order by rank. So if we know that there's $1, and we know there's 4 A's, then we know we have to skip over the first 5 rows to get to the row we're looking for. And because this is the B with rank 1, in other words, it's the second B, we know we also have to skip over one of the B's in the B section to get to where we need to go. So we need to go down by 1 plus 4 plus 1 equals 6 rows. So we're looking for a row with index 6. And we did that without looking at F, but now that I'm showing you F now, and we can confirm, yes, indeed, the B sub 1 is in row 6. But again, I could take away f. I could take f away, and we still know that we have the right answer. 1 plus 4 plus 1 is 6, because that first column has such a predictable structure. So let's do another example here. Let's say we have a much longer t, and we know that that t has 300 A's and 400 C's and 250 G's and 700 T's. And again, this is the ordering of our alphabet. $sign comes before everything else, and for A, C, G, and T, we'll use alphabetical order. So which row in the Burrows-Wheeler matrix for this text T begins with G sub 100? Right, we're using the B ranking again. So which row has G sub 100? Well, again, we know we have to skip over the $sign, and we know we have to skip over all the A's, and we know we have to skip over all the C's. So we've already skipped over 701 rows. And now we want the G that's of rank 100. In other words, 100 G's came before that. So we have to skip over 100 G's. So we skipped over $sign, we skipped over 300 A's, 400 C's, and 100 G's, which means we need to skip 801 rows. So the total adds up to row 801. So we know which row begins with the G of rank 100. Again, not by looking at the first column, but just by understanding the structure of the first column and then counting up. Basically, we had to know the totals for how many times these lexicographically prior characters occurred. But after that, we just summed everything up, and that gave us the row that we're looking for. We know which row begins with G sub 100 after this very simple procedure. Okay. So now we're ready to talk about how to reverse the Burrows-Wheeler transform. We're going to use the B ranking again. So you can see I have the B ranking here. I'm showing you the last column, L, and I'm showing you the first column, F. And here's the procedure. We're going to reconstruct the characters of T in right to left order. So we're going to start all the way at the end where the $sign is, and then we're going to work our way left, reconstructing T character by character. So one thing we know right off the bat is that the first character in the F column is always going to be the $sign because of how we've sorted the matrix and because $sign is less than all the other characters in the alphabet. So since we know that first row begins with $sign, what that means is that the character in the last column of the first row, because the first row is a rotation, so the last column, the character in the last column of the first row is the character that comes right before the $sign. In other words, it's the second to last character of T $sign. Okay, so we're on our way. We've reconstructed the $sign, and we know that the character that comes before the $sign is an A. In our B ranking, it's the A of rank 0. So now the question is, can we keep going to the left? What's the character that comes before the A of rank 0? We can figure that out. The LF mapping tells us that the A of rank 0 here in the last column must be at this position, right? It's the first A. So if we want to know what row begins with the first A, all we have to do is skip over the $sign. It's the first A, so we don't have to skip over anything else. We just have to skip over the first $sign. So the A of rank 0 in the first column appears in row 1. So here it is. Since we know that, now we can look at the character in the last column of the second row, which is B sub 0. And again, since the second row is a rotation, we know that this B sub 0 is the character that comes before this A sub 1 in T. So we've walked one more character to the left in T, and now we've reconstructed the last three characters of T. We know that it's B, A, $sign. And then we can repeat this process. So here we have the B of rank 0. So which row begins with the B of rank 0? Well, we have to skip over the $sign, and we have to skip over all four A's. So it's in row 5. 0, 1, 2, 3, 4, 5. There it is, the B of rank 0. So we hop there next. And again, because this row is a rotation, we can look in the last column of that row and see the character that precedes the B of rank 0, and that's the A of rank 2. So you can see we're reconstructing T step by step by using the LF mapping to hop to the row that's next, and then jumping to the last column, which tells us the next preceding character. And we can just iterate that. So we hop from the A of rank 2 to the A of rank 2. What comes before the A of rank 2? It's the A of rank 1. Hop here. What comes before? B of rank 1. Hop here. A of rank 3. Hop here. And then we're done, because we can see, first of all, we know how many characters are in T. So that's one way we know that we're done. But then also, once we make it to this row, we can look in the last column and see that $sign is there, and that tells us we've wrapped all the way around. So if you write out the characters that we encountered along this walk in reverse order, they are the following: $, A sub 0, B sub 0, A sub 2, A sub 1, B sub 1, A sub 3. That is indeed the original string T. Now, it's important to note, what did we actually use while we were going through this process? We used the information in the last column, so we needed this, all this information, but we only sort of needed the first column. All we really needed to know was basically how many times does each character occur, because that information, in conjunction with knowing a character and its rank here, tells us exactly where to jump, which row to jump to when we're going from one step to the next, because of because of the B ranking and because of how predictable this first column is, given that we're using the B ranking. So we don't really need to store this column explicitly. We can just store the number of times each character in the alphabet occurs within T, and that's enough to let us proceed through this algorithm. So we reversed the Burrows-Wheeler transform of T. We got back T, and most of the information we needed was just this column here, but we used a little bit of information about the first column, just the sum of the character occurrences. There we go. Now we can reverse the Burrows-Wheeler transform. Here's another way of visualizing what we did, except for now I've arrayed it out so that I have many copies of the first and last column, and you can sort of see us traveling from row to row, and you can visually confirm that we visited every row over the course of that process. So here's an implementation that actually does what I just described. It does it in a few pieces. So this very function here, this very first function here, rank BWT, this takes a BWT string. It takes an already Burrows-Wheeler transformed string called BW, and then it returns a parallel list of ranks. So I said before that we were not going to store the ranks explicitly, that the ranks were mainly for illustrative purposes so that we could see what was going on after permutations had occurred. The way we're implementing it here at first, which is a naive way to implement it, is we are going to explicitly build an array of those ranks. But as you'll see, we'll fix that later. We'll take away this array of ranks later. But just because we want a simple conceptual implementation first, we are going to explicitly calculate a parallel list of ranks. So that's what this function is doing. This function here is essentially taking an array which is the number of times each alphabet character occurs in the string T, and then it's doing basically a prefix sum, which is a useful way of preprocessing that information so that we can very quickly jump over all of the characters that are lexicographically prior to some character that we're interested in. So for example, if we're trying to jump into the G section, we want to skip over all the $signs, A's, and C's, and so we can pre-calculate how many $signs, A's, and C's there are so that that's a simple lookup, and that's basically what this function here is doing. And then finally, here's the function that actually reverses the Burrows-Wheeler transform. So we're going to go get those ranks, we're going to go get that pre-processed version of the number of occurrences of each alphabet character. We're going to start in the first row. Here's our partially recreated string T, which we're going to repeatedly prepend to as we recreate more characters. And then here's our loop. Basically, we're going to keep going until we see a $sign in the last column, like we said before. We're going to get the character that's in the final column of the row that we're currently in. We're going to prepend that to our answer so far. And then we're going to calculate the next row to go to. basically by jumping over all of the rows that begin with lexicographically prior characters, and then jumping over a few more rows according to the rank of the character. So if we have the the B of rank 1, we're going to jump over the $ and all the A's, and then we're going to jump over one of the B's. And we're going to iterate this again until we see that $ in the last column. And at the end of the day, we'll have reconstructed T. And you can see this code in action if you follow this link here. This is an IPython notebook that shows this code. I will show you a few examples. So you may not remember, but earlier we calculated the Burrows-Wheeler transform of this string here, and we got this string here. And so now we're just reversing it. So we're taking that same string, passing it to this reverse BWT function, and we get back the original string. Likewise for this example and this example. Now, like I said, we said that we weren't going to explicitly store these ranks, but for this particular implementation, that's exactly what we did. And that's unfortunate because this is an array of up to m integers. This is an array of m integers. That's a lot of space for us to be taking. We don't want to take that much space. That's as much space as the suffix array takes, and we will ultimately want to take less space than that. But we will fix this later. We will make it so that we're not explicitly storing an array of m integers as we refine this later on. Okay? So when we first introduced the Burrows-Wheeler transform, there were sort of three mysteries that we had to solve. We had to figure out how it was useful for compression, and we showed that. We had to show how the transformation was reversible, and we just showed that. And now we have to answer how it's used as an index. And we'll take a look at that in the next video.